Okay, so this is a supplement. Once you know implicit differentiation, you can prove that you're allowed to use the power rule with rational exponents. In my class, I think it's best to only use things once we've proven them. So, the power rule works for variable base and any exponent. We start off at the beginning kind of proving through example the derivative of like x squared, x cubed, x to the fourth, and then extending that to all positive exponents. And then once we have the quotient rule, we can prove that we can use the power rule using negative exponents, x to the negative second, x to the negative fourth power. So now that we know implicit differentiation, we can show, prove, however you want to say that. We're not really going to do a rigorous proof, but that's okay. That we can use the power rule with variable bases and rational exponents. So we're going to start off with x to the power 2/3, which is definitely a power rule situation, variable base x, constant exponent. But let's assume we can't use the power rule. Let's rearrange so we don't have to use the power rule. And really the problem is this 1/3 exponent. So to get rid of that, we're going to cube both sides. And maybe I should write that in. So, right, if we cube y, we get y cubed. If, we cube x to the 2/3 power, we get x squared. And so now you can see, well, we've removed that rational exponent situation. Y cubed, we can do the derivative of something cubed. X squared, we can do the derivative of something squared. So the derivative of x squared with respect to x is easy. That's 2x. The derivative of y cubed is definitely 3y squared, but there's a chain rule, dy dx, as in the derivative of that y. Okay, so we're looking for dy dx. That's the piece we want to keep. So we'll divide both sides by 3y squared. And, maybe we want to think where we're going so we can figure out the algebra that we should do. And, if the power rule works, and it does, for an exponent like 2/3, we expect to get 2/3 x to the, negative 1/3. 2/3 minus 1. Okay. And so we can see already, well, we have that 2/3. And who knows about the x in the numerator, but we really want to rearrange to get rid of that y that's being squared in the denominator. So let's replace that y with what y is equal to, x to the 2/3 power, way back here from the beginning, because each of these y's, each of these x's all represent the same thing, right? All the x's refer to the same x, as in if x was 2, all of these different x's would have to be 2 at the same time, that sort of thing. Anyways, so now we need to, I guess we're going to leave the 2x. We're going to leave the 3 in the denominator. X to the 2/3 power squared is x to the power 4/3. Let's get rid of all of this. All right. And so now we're getting closer. We want, we have x to the first power and x to the 4/3 power. So we can just rewrite that as x to the power 1 on top. Let me give you a 1 just in case you need it, minus that 4/3 power on the bottom. And we indeed get 2/3 x to the negative 1/3 power. So at least proof of concept, that works. Okay. So if we want to do that for anything, you could imagine if this was the 3/4 power, if this was the 5/7 power, we could basically do the same process. If this was 3/4, well, then we're going to have a 3 where the 2 is and a 4 over here, but kind of the same process. So let's go ahead and show that the power rule works for variable base and any rational exponent. So we're going to stipulate that a and b are integers. If you want, you can make them positive integers, but whatever. And so same sort of thing. We want to get rid of that root, that 1 over b power. So we raise both sides to the power b. And we end up with y to the b is equal to x to the a. And since a and b are exponents, that's like y cubed is equal to x squared, or y to the fourth power equals x to the fifth power, something like that. And we can definitely use the power rule for exponents like that. And so the derivative of x to the a is going to be a x to the power a minus 1. Similar thing on y to the power b, but don't forget, we need the chain rule there. So not only do we get b times y to the power b minus 1, but we multiply by the derivative of y, dy dx. And we're kind of thinking back, oh yeah, I want to keep this dy dx by itself, so we'll just divide everything by by to the power b minus 1. And just like when we had something a little more concrete, let's think ahead. Where are we going? When we're done, we're going to have dy dx is equal to, well, a over b times x to the power a over b minus 1. Right? That's what we're trying to prove. And you can see we're at least semi-close. We have that coefficient a over b ready to go. And so the thing that doesn't belong again is this y. This y in the denominator, we're going to replace with what y is equal to, x to the power a over b. And then the algebra gets a little bit hairy. So a power raised to another power, we're going to multiply exponents. And hopefully that makes sense to you. Maybe you could think of that as x squared cubed. Means we have 3 versions of x squared multiplied together. So that would be 6 x's altogether. Let me get all that junk out of the way. We don't need notes. Okay, so what do we end up with? Well, the a over b I've popped out front, so we don't have to think about it. And still x to the power a minus 1 in the numerator. In the denominator, the a over b times b gives us a, and a over b times 1 gives us a over b. And then we're going to do what we did when we were with concrete. Was that x to the 2/3 power, I think? Or x to the 3/2? 2/3, I think. Whatever. We're going to subtract exponents, right? So x to the power a minus 1 in the numerator power minus a over b down here. And you can see we're going to get a minus a is 0. And you know, minus 1, we don't want that out front. We're going to put the minus the negative a over b out front. And we indeed get what we're supposed to get. And that is, hey, the derivative of x to the rational exponent a over b is a over b x to the power a over b minus 1.